Hi everybody and welcome to this session about IDA Memory Snapshotting. We will use this feature during the debugging, of course, and I will try to show you this feature on a practical example of Amadey Malware. Amadey is actually a well-known malware family. It's a bot, and I will try to show you how you can unpack this bot, the Amadey sample, right, and purely in an IDA Pro. We'll be leveraging the feature of memory snapshotting. I will show you a different option of memory snapshotting in IDA during the debugging, how it's a very useful feature, and also things like things you are commonly probably doing in x64 debugger, but you can use IDA Pro for that too. I would like to also mention that there is a new addition to this feature of memory snapshotting. Before releasing of 8.2 version, there was only there were only option to take a memory snapshot of all segments, lower segments, but not like a separate specific segment, which was quite not good. I will explain later on. So first of all, we will grab the Amadey sample. I will include all of the links I will show you here below this video, so be sure that they will be there. First of all, I will be using, or I come across this analysis from my friend Matthew. He is available on Twitter, I think. Yeah, you can see here on Twitter. He's an engineer and malware researcher. He's sharing very nice and tricky and very cool analysis. But what I wanted to show you actually is one of his posts was about he called that redline stereo static analysis and C2 extraction. It's actually the post is about unpacking and C2 extraction of Amadey, but this is not like bad or incorrect naming of the article, because the redline stereo is actually also packed in the cap file where also the Amadey is located. So just the cap is a bunch of malwares, more like both a redline stereo, both also like Amadey, so pretty cool. Uh, he covered many things here. He used mostly x64 debugger and Ghidra, but today I will try to replicate some steps of unpacking just purely on IDA, leveraging the IDA memory snapshotting. So this is just about the post. You can see here also you can grab the sample. This sample we will be using here today. Something about the memory snapshotting. IDA has in documentation something about that feature, and it actually tell you that this feature is enabled, you can use this feature of memory snapshotting during the debugging session, so you can snapshot the database in the state where the segments are used for debugging stack, and for also the loader they change during the debugging, of course, and you can actually capture a snapshot of that state, and it will be saved in IDA database. So pretty cool feature. I really recommend it, because if you have some unpacking shellcode or self-unpacking executable which will modify itself in memory, it's very useful, because you will just hit the snapshot just right after it will be unpacked or modified in memory. Um, Here is also that you can also edit segments, yeah, because with if you just snapshot some kind of segments or all segments, sometimes you need to edit some things like name of the segment, attributes of the segments, and other things. So here is also the section about the segments. Memory snapshotting in IDA is has its own history. It's not some new feature. It's very cool, but it's not new. But what is new? It actually came in 8.2 IDA release. Somebody asked me how I found out this. It's really tricky because there were many highlights, because IDA Pro brings us every day or every release very cool features. But here it was actually a little bit hidden, and for me it's a very interesting feature. For me it's crucial because I'm using it a lot. So if you scroll a little down, there is a like note about that there is something what was added, and it's here: user interface edit an easy way to take memory snapshot of current segment, which is cool. I will explain why it's really cool, because before this release you could just take a memory snapshot of all segments, which will result in a large database, or just load the segment. I will explain it. Right, just we can just jump to it. First of all, there is the sample, extract files, infected. You can see it here. Here we have some file, which is a cabinet file. If you just try to detect easy, cabinet, so we can extract it with 7-zip extract files. Okay, and here we have two files. Again, this is our packed Amadey sample. But what is that? This is actually another cabinet file, so we can extract it. Okay, again. And what is that? Here you have another sample and another cabinet file, and you can go on, keep going, and keep going, and it's like it's boring. So, but I would like to explain why the naming of the article of the Matthew named it with a red line, because there is actually sample a red line, and because of that the cabinet file was like marked to be like related to Redline malware and not Amadey. So just to show you, we are not here today for, unfortunately, we are not today for reverse engineering.net. Yeah, I know you know me before because of the .net, but yes, trust me, I can still find the shortcut of IDA Pro on my desktop. Here you can see the main function, and redline is quite known to be like there is function writeline, which is not writeline, and here is a typical configuration of the redline stealer. Great. So we are not interested in this at all. So just grab the packed Amadey sample, copy that, and put it for the name sample. How I found out that it's packed? Take it easy. Let's check entropy. Entropy is one of the crucial factors we can check, and we can see that entropy is somebody. Very often people are showing just whole bunch of like all section entropy, which is not really like something what is crucial. The crucial is the code section, and if you mark code section, the easy will just highlight the section, and you can see that the code section is really has a high entropy, which could be some kind of sign that this sample is packed. You can see also the easy is marking it like, hey, it's back. Be careful. Another thing how you can check it is probably strings. If you check strings in Detect It Easy, you can see that there is a bunch of strings. Yeah. So, but not many. It means that it's actually not packed. But another thing how could check it is are imports. And if you check the imports, this looks like some kind of nonsense things, and there is only like kernel 32, but it actually could mean that the resolving of APIs occurs during the runtime, so not a mark of it's really being packed. But high entropy, not much relevant imports. Also in import table there are function for like virtual allog, virtual protect, so it's could be some kind of mark that this is some kind still it's packed, so we don't want to bother with packed sample, we just want to grab the final result, the unpack Amadey. So we can start. First of all, what we can do, we can just put it into IDA first. Yeah, again, it's a 32-bit sample. Still, I will be using a 32-bit IDA Pro. Okay. No PDB. Huh. Interesting. Well, and we are on the main function. Great. It's not large. It's relatively small. But what we can see here, there are some interesting imports, as I already told you. So, for example, virtual protect. Virtual protect. Let's check the cross references, and we can see that it's called only from one function. Let's decompile and check it out. So what we have here? We have here some address, which is assigned to some global variable, and this address will the protection of the memory of this address will be changed to be read write execute with some kind of margin, maybe some kind of shellcode will be there. Where this address from where this address came, we can check it here. Maybe no, it's here. It's here, but I would like to find out where it get assigned. Right, it could be, but it's a nonsense. Uh, nope. Yeah, maybe the right could be like good decision. Yeah, but you can just load the effective address of that and something like that, assign later on. So here you can see that it get assigned global alloc, some size, and it gets assigned. So nice. From where it is this code? From the same function. You can see the virtual protect, and just above that is the allocation. So we can consider that there will be some unpacked shellcode. If you check the references, we already got to that point, but you can check it here that it will be called. Yeah, so it will be invoked. It could actually mean that it's very high chance that it will be just some kind of in-memory unpacked shellcode block, or maybe the Amadey itself. We will find out. Super. So what I think now is the time that we will just put a breakpoint in WinMain function, local Windows debugger. Oh, sorry, Windows debugger. Put a breakpoint on WinMain. And as we check that there is a virtual protect somewhere. Yeah, it's from different function, but here, I think. Yeah, here is the virtual protect, and right below, one of the last instructions should be here. It gets invoked. So let's put a breakpoint on this too. Why? Because there is a high chance that on the allocated memory there will be already unpacked shellcode or something like that. We can start debug. Let's start, and yeah. So I will just make this a little bit better. We don't need this window. We don't need threads. Yes, that's better. So first of all, I would like to typical and very tricky thing. As a normal reverse engineer, I will just try to put a breakpoint on some cool things like virtual, typical associated with some unpacking. Oh, here put a breakpoint and virtual protect, because we saw that virtual protect is actually used. Great. We have two breakpoints and we don't need this window anymore. And 2. Nice. We can continue. and we hit the breakpoint on virtual protect. If you remember, once the virtual protect is called, the return address is pushed on the stack, and we can see it here on the stack, like the location of next instruction right after execution of the virtual protect. So let's double click it and we will get to this point. If we check it, we are just in this location. Great. So what we can do, we can check the address, which is one of the argument. It should be like here, fourth argument, probably. Oh no. Here it is. If we check that, yeah, it's actually first argument to virtual protect. I can see that now. Here, yeah. Let's back, and we can continue, and we should hit a breakpoint before the invocation on the newly changed protection of some kind of memory before the invocation of it. Just continue, and we are here. Yeah, before we jump to that address, you can see that it got populated with something which starts E8, typical some kind of shellcode instruction. We can jump to that. F7, and we are here. It's a segment which is called debug 059. And here is the start location. You can see that the shellcode start, like the point of the start, is not immediately in the start of the section, which will be quite interesting because I will show you. Now we are somewhere here. What we would like to do, we could capture just this segment. So how to do that? Go to view, open subview, and here is the segments tab. Segments tab, and we are immediately in the debug 059. Yeah, remember debug 059. So first of all, I would like to rename it. Yeah, so you can actually edit segment. You can edit some attributes and others, but I would like to edit just the name shellcode 1. Okay. We can jump back, and now it's time to explain the memory snapshotting feature of IDA Pro. You can go to debugger, and here is the option take memory snapshot. You can see here are all segments. We are not interested in them. Here, if you just go to debug and debugger and take memory snapshot, you have three options. Very common options, all segments, lower segments. But what is new and was added in 8.2 version of IDA is current segment snapshotting. Very cool feature. Because all segment snapshot, what it will do, it will capture all these segments, stacks, debug segments, and others, basically some kind of trashes, and it will save it to your current IDA database. So once you stop debugging, after you take memory snapshot of all these segments, it will be all populated in your IDA database, and your IDA database could be very large. It will result to be really large. It's good in some when you want to have everything in a database, but in more sophisticated programs, you just it can happen that the database will have like few gigabytes, and it's pretty bad. What you want to do next time, later on, usually, is to shrink the database. So what you will do after that is something like you will try to remove those segments, and after you remove them, the database needs to be shrinked and or shrank. and it takes some time. Yeah, it's quite time consuming, and I don't want to bother with that. I don't need all segments. I just need one specific segment, which is called shellcode 1. Yeah, other than that, there is another option. There is another option which is before the introducing of the feature of current segment snapshotting. I was using very often the all segments, and I was later on removing those segments I don't care about. And other than this option, there is another option to take memory snapshot of loader segments. What is loader segments? Lower segments are segments which are having an attribute L as a loader, and you can see there are only 3 segments which are actually assigned to our main module sections. Yes, that's cool, because IDA loaded, Windows loaded, and it was started, the debugging session was started in IDA Pro. So IDA automatically marked these sections to be as a part of loader. This is cool, but remember, if you attach the IDA Pro to some process already running, even though there is main module, it will be not marked as a loader, LLL, like with the L attribute, because it was not loaded by the IDA, there was no initial analysis and other things, so no mark as loader. Why this is pretty cool to have this option too? Because very often, the malware is unpacking into itself, like for example, self-modifying instructions or a shellcode blob in the data section, which has also attribute like that it's a read, write, execute section, or for example, you have text section which is read, write, execute, and if you have text section like code section which has memory protection of writable, it's very suspicious, because it can actually write to itself, modify itself. But exactly for this purpose is the feature of taking memory snapshot, of lower segments, because once you get after the point the code section is unpacked in memory and it is part of the loader segments, you can actually just take snapshot of the loader segments right after this unpacking, and what you will have in an IDA Pro database is the the end result of this unpacking. Yeah, so the modified code, you are interested in the unpack code. So very useful feature, I'm using that very often. And the last one, which is the newest one feature, is current segment. Remember, you need to be focused like in the current segment. So here, for example, I'm on shellcode 1 section. I renamed that segment, and I will just capture the current segment, which is shellcode 1. If you will be somewhere different, you will just you will be taking a snapshot of the segment where you are located in the disassembly view. So remember that. Just press OK, and now we have saved this segment in our IDA database. So if I just stop the debug, if I would stop debugging, it will be saved in the database even after the debugging. Yeah, so it's pretty cool. Also, it's important to note that if there will be some modification in lower segments, like for example in the main module code section text, you will not propagate these changes into your database if you won't save it. So for example, you need to save all segments, or you need to save lower segments to propagate these changes to IDA database after the finishing of debugging session. Yeah, so this is just like, for example, you start debugging, and if you stop debugging, nothing is modified in your IDA database, normally, defaultly. But if you take memory snapshot, be careful, these things are modified. Great, we just took a snapshot of the first some kind of shellcode blob, which is super interesting. But we can see there is some call, other thing, blah, blah, blah. So let's continue. We hit another another API call virtual alloc, but from where? And you can see that it again return address is on stack. So you can see that it was called from the shellcode 1 segment, which is pretty cool. So there is some allocation from the shellcode 1. Let's jump to it, code, and you can see it's the return address. This should be some still some instructions. Now it's maybe better. Yeah, here. Here you can see that here is some call. This call should be to virtual alloc. If you double click on it, we are somewhere, but it's an offset. If you press O, it will be changed. The bytes, those bytes will be changed to an offset, and it points to the virtual alloc where we are. Great. So once again, go here and put a breakpoint on return. Yeah, because virtual alloc will allocate some memory. The allocated memory, sorry, I didn't show you, but it was read, write, execute, which is some kind of mark of that it will be suspicious. You can actually verify that because the return address, which was already allocated, is in EAX register. EAX register. This is the address 223.00000. Segments. Try to find the address 0202223.000, and you can see read, write, execute. Great. So it will be probably some kind of another shellcode, or maybe our Amadey sample, which is just allocated with read, write, execute. We don't know. We don't know. So what we can actually do is still be careful, because this is a little bit confusing in IDA Pro, and because of this reason, many people are using X64 debugger. It's the navigation between the window, but it's super simple. Just stay focused in hex view, and if you want to focus on some address, for example here, the AAX, which is the newly allocated memory read, write, execute, just click on it, and you are here. And it's still empty for now. But if we will continue, like stepping over F8, 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 and here is some function. With this function, which will actually populate. Surprise, surprise! I tried that before the recording of the video, but it was really fast. I tried to prepare it in a short time because I was asked to prepare it. Press step over, and something was allocated, and it again looks some kind of blob of shellcode. I'm not sure. You know, I'm seeing hex view, the same hex view as you, and I'm not so good like I see hex bytes and I immediately see assembly instruction. No, I don't have any kind of disassembler in my head, but we can step over, step over, step over, step over, and here is some kind of jump. Where it is jump to. If you double click, here is again some bytes. I have a suspicion that it's an offset. Press O, and you can see some location 223.000. 223.000. So this is probably some kind of another shellcode. Let's jump back and press F7 to step in. And we are here. Jump, and you can see both of those shellcode are actually like made. Usually good shellcode nowadays, almost every shellcode is made in a way to be workable like in memory independent addresses, because of the ASLR, like memory randomization and other things. It's just being made to be able to execute from any kind of location, which is pretty cool because we can emulate it independently if we dump those shellcode. I will show you later how to do that. So we are somewhere on the segment debug 061, which I think is another shellcode block. If you check, it's actually a start. Yeah, so this now this shellcode will start just from the beginning. Like the execution of the shellcode. So again, what you can do is go to segments and try to locate debug 061. Segments, debug 061. It's here. Read, write, execute. Correct. Yeah, if you check that, you are here. First of all, just rename it. Shellcode 2. Okay, so we have shellcode 2. We are focused in this segment, shellcode 2, and what we want to do, we would like to save that in our IDA database. So once our memory debugging session will finish, it will be saved in our IDA database to later reverse engineer that or investigate and other things. So debugger, take memory snapshot, and current segment. Yeah. Okay. And it's saved. Yeah. So that's pretty cool. We can continue because remember we still have breakpoints on virtual alloc, virtual protect. And I don't think Amadey is actually shellcode. It's an PE file. So let's continue. I don't care about that. We will just emulate this later on. I will show you it will be really fast. Continue. And we hit another breakpoint, virtual alloc. Virtual alloc. If you check those arguments, I don't remember, but this one is like for memory protection, and 4 stands for read write. Read write. If you check from where it was called, you can see the shellcode 2. So shellcode 2 was doing something, but in the end of doing something, it allocates another memory. Maybe it will be interesting. We don't know it. And here is the location where it returns from the virtual alloc to shellcode 2 segment. Just press C as a code, and it's some kind of middle of function. Yeah, this is actually finding the start of the function will be like super guessing. And I really don't know. Maybe try to find a bunch of nulls. Yeah, here it is. It looks good for me. Yeah, it looks good. We can. Sorry. Once again, I press C, like to change it to code. C, and I press P to create a function here. Well, now we have somewhere you can see in function here. Why I did that? Because I want to see a graph view. Why? I will show you why. So we are in a state that something is allocated. So press F2 on return address from virtual alloc. Continue. Well, and we are here. And in AAX register is a newly allocated memory 227000. So just stay focused on the hex view, because if you did this, you are focused on the disassembly view and press this, you will jump in disassembly view, and we don't want that. Yeah, we want to check how this memory will be modified during the execution. Yeah, and we are here. Pretty cool. Now I wanted to show you this segment, because if you are not sure or don't remember how it was allocated, like what are those memory protection which were specified during the virtual alloc call, is that you can see those that address 22700000. This is actually start of the segment. Yeah, the start address, which should be somewhere here. 22700, you can see here. 2270000, 2270000. Read write, read write. There is no execute. We will see what will happen. What will happen? Let's continue to execute. And this is the reason why I switch to graph view, why I create a function, because without the function you can't just see a graph view. Check it out, because without that you would very strangely see that there is a loop and something is happening. Change that. Check this newly allocated memory. Something is happening. You can see the loop. Yeah, and you can see some MZ header. Whoa! Surprise, surprise. So probably this is some routine responsible to write our unpacked Amadey sample to some memory location. And surprise, surprise, there is a high chance, because it was allocated as a read write, that this sample will be written in memory, like here, in a raw format. What I mean, it's not virtually mapped. which will save us some kind of time that we don't need to repair that. Yeah, because if the sample or if the piece is already mapped in memory, virtually mapped, it means that sections or segments are virtually aligned, and you need to realign it to some kind of to be, because on disk and in memory it's different. If you don't know, you can check some video from OLAPS. They are pretty cool, and one of the latest videos was about PE mapping and unmapping and difference between them. It's very simple, but I suspect that this will be not virtually mapped, which is cool because we could literally immediately analyze it. So there is some kind of loop. Here is the only one branch which is out of the loop. So let's put a breakpoint here, continue, and check it out. Yes, this looks that we successfully unpack it. Maybe fully, I don't know yet. If you check that, now we confirm our suspicion that basically it's not virtually mapped, but it's a raw thing. So what I think is actually that it was written in a memory section, yeah, which was newly allocated, unpacked, pushed there into the section, and from there it will be probably mapped virtually to another allocated memory. We don't care about it because we already have it in a state we want. But we need to confirm that we are in a state that it's ready. Yeah, it's ready. It's all like all data is there. It's all the PE is it's whole. So how to do that? You can, first of all, you can check that here is a DOS header. Yeah, here is like headers, and usually section aligning, virtual section aligning is it's specified in a PE structure, but usually it's like 1000 hexadecimal bytes. Yeah, so if you will see that here, for example, it's some kind of ending. Here you can see 400, which is like typical address where text or code section, first section after the PE headers start, and it's 400, which is some kind of mark that it's not virtually mapped. But we will make sure later on. Great. Just come back to that, and remember the segment is 227000. Segment, go to 22700, and we don't know. Okay, here we don't know if it's fully unpacked, so we can actually investigate immediately in the IDA. Yeah, so what you are doing, one of the first action you are doing to check if something is still packed or not fully unpacked, not fully written, we will just check some strings. View, opens view, and get me strings. Be careful, probably it will be calculated on database, but we will focus on the debug 062 segment. So let's filter that debug 062, and we are here. So there is bunch of strings, and you can see here that there are some strings which looks like encrypted strings. Okay, it looks like encoding, base64 encoding, but it's not a pure base64 encoding. It's like another encoding is added to base64, which is like working with some key and index. It's not important. We are not care about that here. But you can see it looks pretty unpacked. What you can see next, it's actually a PDB path. Wow, it's actually tell us it's Amadey. Ooh, surprise. Nice. So Great. I think that we are pretty sure that we have everything here. It should be probably unpacked. Yeah, because there is a bunch of interesting strings and other things. Right. So what we will do next? Surprise, surprise, we will save this segment. First of all, I'm here on the segment. We can rename the segment so we can recognize it later on very easily, and we can rename it to Amadey. Okay. Let's go back to the segment. And now, again, debugger, take memory snapshot, just current segment. Yeah, and okay. Now we are in a state we can stop the debugging. Why? Because we have the original loader segments, our main module. We have shellcode 1 segment. We have shellcode 2 segment, and we have something we have such position that is already unpacked Amadey segment. So let's stop it. And surprise, surprise, go to view, opens view and segments. And you can see it here. You have here everything. Yeah, for example, jump to Amadey, and here is the Amadey. If you check it here, it's super cool. And I know, really don't tell me, but I know that most of you guys absolutely don't care much about this first line. But it's pretty interesting because this is showing the IDA database memory, and different kind of color stands for different kind of data type or code type or library functions or unexplored and other things. But here it's really interesting because here you can see that something is like a little bit analyzed, yeah, or something like that, and it's a loader. This stands for the loader segments. Here you can see here is the data section, data segment of the of the main module, but here starts the section of the shellcode 1. Well, it's collapsed, yeah, but we don't care. Here start the section of shellcode 2. Here start the section of Amadey, the segment of Amadey. This is pretty cool because we will use that later on. So what we can do now is that we don't care much about the initial segments. So for example, if you just jump to text or code section, you see something like this. Now, of course, you can save the database now. Yeah, you can save it or you can do whatever you want. But you have everything here. Everything just in a pure IDA. If you now there are options to remove those segments because we don't care about them. I want to focus or extract things from these segments or something like that. This is not important for me. So I would be here, for example, like focused on code section, text section. And if I just try to remove that, delete the segment, there are two checks. Confirm deletion, okay, you need to confirm. But there is another check, disable addresses. What does it mean? If you do this without disabling addresses, it will be deleted. You can't see anything, recognize code, because what just happened? The definition of the segment on the specified memory range was deleted, but just the definition. What does it mean? If you check the IDA view, there are still data, those bytes which were originally in a code section. Yeah, so it's still present in the IDA database. Why? Because it could be very neat, cool, and IDA decided to do it like that, and it's really cool that you can remove the segment definition, and you can, for example, define 4 different segments on this memory area, which is still populated with the same data. But this will actually result if you delete segment and now you think, I have a much smaller database. It's not true because you can see the data are still located in the database. And if you want to really shrink it, you need to remove these two. Yeah, remove the data, so you need to disable the addresses. And disable addresses actually mean that they are free to be allocated or allocated on other things. So redo, you can go to edit and undo delete segment or Control Z, and here you have. If you jump here, you are here again. Just right, delete, no, delete segment, and now confirm and disable addresses. Okay. Go here, and you can see that code segment absolutely disappeared. Yeah, because you have IData, data, no text section. Yeah, great. So we would like to do this also with the another loader segments, which are part of the main module. We don't care about this. It was related to unpacking. Delete segment, confirm, and disable addresses. Okay, great. Now we have shellcode 1. Great. Just put what I would like to do now. I would like to grab all these segments and save it to binary files. Like what you would normally do in x64 debugger, just save the memory to some file. Here it is a little bit more tricky, but I will show you how to do it in a relatively fast way. Click here and begin selection. Yeah, you begin selection on the start of the segment, and you need to find now where is the end. So you can actually go here, copy the end address, go and navigate, but other than that. So, but I already show you this special window, and if you focus somewhere in this, which is should be in the end, like very close to the end of the shellcode 1 segment, you are here, and this is the end. You have selected it. Go to edit, export data, and raw bytes. Select location. We will call it a shellcode1.bin and save it. All files, save it. Shellcode1. Raw bytes, shellcode1, export. Just check it. Shellcode1 is here. Great. Check it in a hexadecimal editor if there is no mistake or something like that. Remember, shellcode 1 started the execution in somewhere in the middle or somewhere, not from the start. Yeah, but to verify very quickly if we correctly done that, just take some strings, and you can see there are some strings related to it, but I don't know it's really if it's correct. Hopefully it's, it looks correct. It looks correct. Great. So we have like selected the shellcode 1. Abort selection. We will do the same for the shellcode 2 segment and for the Amadey. So abort selection, go to segment, shellcode 2. We are on the start of the shellcode 2. Just edit, begin selection. Go to, you can see we are here on the start, go to the end. And we are in the end, and now we have selected it, and edit, export data, and raw bytes, location, all files, shellcode 2. Shellcode 2, save that. Export. Let's check it. Here it looks quite good to me. Yes, it looks good. Surprise, surprise! The shellcode 2 is actually containing not just some blob of shellcode, which is responsible probably for in-memory mapping of the Amadey sample, but it also contained probably the Amadey sample itself, which is pretty cool. Yeah, I didn't know that about it. Because if you check the PDB path, it's there. Also in the shellcode 2. Great. But we want to have it correctly to be dumped, like right in the database or here abort selection, go to segment, start of Amadey. Now you can edit, begin selection, and you can go right to the end. Here. Great. Go to here, for example, edit, export data, raw bytes. Here, location, all files, and we will call it amadey.exe. Okay, export. Don't forget that you didn't export it yet. Export. Now check it, and if it looks good, yeah, it looks like PE, everything's okay. Great. Abort selection, and don't close it because we are not sure, maybe something could be corrupted or something like that. We will find out it. So first of all, we have a first shellcode1.bin. What it does? As I told you, the shellcode1, I think the shellcode1 actually didn't start on the memory, like start of the memory segment. So we can just use a tool. I will go to my tools, debuggers, shellcode debugger, scdbg, very cool, because it's a 32-bit shellcode. We can actually emulate it. No, we can, well, we can drag and drop. And we don't know the offset. I don't remember. I didn't note it. Yeah. So what we can do, we can just find shellcode. It will try to brute force all location and it will tell you what it suggests and other things. So launch, and here you can see it start doing something. Oh, sorry. I can see what happened. I actually put there not the shellcode but the Amadey sample. So shellcode 1. It should be much faster. Yeah. Launch and find shellcode. And here we are. You can see that we are 4 different indexes, which suggest that it goes to load library A. So what we want to select, maybe index O, because it's the first location, yeah, the nearest. And you can see that it goes to low library, get proc address, and you can see global alloc, sleep, virtual alloc, create to help 32 snapshot. Maybe it will just iterate from to in processes. Maybe you can see module 32 first. Maybe it will just try to find some that could be related to some checks. Great. So we can try to set those offset, that offset here, unlimited steps, this one, and report mode, launch. Well, something happened. I don't know what happened. O1B, find shellcode. Come on. O1B. Offset O1B. Start offset. Sorry, I didn't mark it. Start offset, report mode, unlimited steps, and launch. This should be okay. Yes, because I forget to actually check that. Yeah, that we want to just emulate the specific offset. And you can see it's still the same, but it will tell you also that, hey, it uses the inload order list and other things. But again, I suspect that this actually virtual alloc you see or something like that, it will do maybe some check and allocate the shellcode too, where it actually transfer execution. We saw it already. So what you can do now, it's just push here the shellcode 2. We can know, maybe start from, we know that it started from start of the shellcode, but you can again find shellcode launch. And you can see offset 0, so index 0, and you can see load library A and virtual alloc, virtual protect, virtual free. Yeah, it's terminate process, exit process, set error mode. So it's very likely that this shellcode blob will do just another allocating of memory for our Amadey sample, what we actually saw. You can investigate those shellcode, you can reverse that more deeply, but this is some kind of initial assessment. So great. We emulated those shellcode. What we have here, I think that I can actually close it, don't save the database. And what we have here, the Amadey sample. But if you open it in PEBur, you will see that there is some overlay. This is a result of because there was a memory allocation, and the memory allocation is always a little bit larger than the real raw size because of a memory aligning and other things. So this is the result. Why is here the overlay? We can try to remove that overlay. Again, if you go to detect it easy, go to overlay, you will find out that the overlay is just bunch of nulls. If you check CFF Explorer, you can see immediately that it will tell you file size is larger than actually the PE size. How you can trim the overlay? You can do it in hex editor. Yeah, of course, you can do it. You can calculate it somehow. You can calculate it via the CFF Explorer. What is the file size? What is the PE size? And trim it like this. The point that it's really in raw format and no virtual map is here. Yeah, it's actually obvious. Well, to be cool and to preserve, to be cool, I will switch to Python. cd change directory to sample, and we will use pfile. Why? Because there is a function. Check it out somehow. pfile pe trim, and you can see return the just data defined by the p headers, removing any overlaid data. Great. This is exactly what we need. So to do it in quick way, I will do things like this. With open, we will create a file, and we will write the data of the original Amadey, the unpacked one, without the overlay data to that file. With open, and here will be like Amadey unpacked write binary sf f write. And here comes the magic, p file, pe, Amadey, and trim. Yeah, that should be okay. Open that, write binary, write the file, which is the Amadey exe, but without the overlay. Okay, and it should be done. Check it out. Here it is. You can see it's more. If you check the PEBur, there is no overlay. And if you check the CFF Explorer, the PE size and file size is the same. Great. So we have it here. Nice. And we are almost finished our video, but I have a little bit surprise for you. I will show you a little bit tricky thing in the end. What is Amadey using to actually initialize its encrypted strings? Nobody is mentioning that anywhere. But for me it's really interesting. I will show you. So we have here this sample. It's already unpacked. We did it purely in IDA Pro with using or leveraging the memory snapshotting. Great. You can see that it's actually 32-bit sample. Just put it to IDA. Okay. You can see a PDB path. No. Yeah, and we are on the main function. There is a little bit quite an interesting thing. It's also mentioned in here in the blog post from Matthew, but he also stated like that those encrypted strings came from nowhere. It's really true. It's really true because there is a neat thing that they are initialized before the main function. So somebody made something to execute code before the main during the C runtime, like initialization and other things. I will explain. So if you go to view, open subview and strings, you will find out that there are a bunch of strings and some of them are those looking like base64 encoded. Yeah, but okay, we will just get, for example, this one. Get me reference to this string. You will find this some kind of function. Well, okay. So I will show you. First of all, we are on the main. First function, maybe there will be some already, because you need to work with strings, so where those strings are accessed. It turns out that there is actually some value, global variable, which is, this is what? This looks, for me, because you know it's taking probably some string, maybe string value, or memory bytes, I don't know, and some other variable, and it will like maybe output it. Maybe there is a move. I already saw this kind of function sometimes, so we can try to apply Lumina meta. Maybe we will hit some point. Great. Go here. And we will try to use Lumina and only pull meta for current function. Okay, we didn't get anything. But I think it's some kind of assignment or something like that. Don't care. So here is something which probably goes to here, and this will be decrypted. This is actually the decryption, string decryption or decoding function. Yeah, it's a modified like base64, but also edit some another indexing and things like that. It's called from 172 location, and if you check, like, what is this? What is this global variable? Cross references, you will find location like this. This is actually the assignment. Yeah, so here you have some thing which looks like base64 encoded, but it's also encoded with other routine, with some indexing and other things. But this will be, because you can see here is the global variable, here is some base64 encoded string, and here is as size, because 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Yeah, it's a size. So I would say like this is like assign this string to this global variable. If you check this, yeah, new memo. It looks like string assignment to me, but we can try again. You can use Lumina pull current function, and you can use also flirt signature. Yeah, because flirt signature for C runtime libraries and other things, and maybe it will match the signature of this function will match some normal C function. So you can see that here it matched. Great job, Lumina. And it's an assigning, string assigning. Great. So you can see that this string is assigned to this variable, yeah, to global. So you have here this some kind of base64 encoded something string. It goes here probably, and here is the decryption function, decoding decryption. Yeah, okay. Where from where this assigning? Oh, from where it is called? Like, because if you wanna work on IDA, yeah, it would be good if you would already have these things in the globals, so you can actually parse it in IDA database statically and everything. Of course, you can debug the sample, get to the point where these global variables will be already assigned. Take a memory snapshot, as I already showed you how you take a memory snapshot, because these dwords are a part of the loader segments. So if you take a memory snapshot of the loader segments after this assignment, these things will be nicely populated. And you can work on that with either Python, statically decrypt, and put some comments of decrypted strings, other things. Pretty cool. But I'm interested, like, hey, what is that assignment, man? Yeah, because what is that? Yeah, from where it is called? Our data? What the bunch of function which are part of some table? What is that? What is that? What is that? From where is it called? Main, sac main. Wow, it's actually before the main. Yeah, it's initialized because you could see that it's a global variable. There are global variables, and these are it's a initialization of global variables. So you can see here that actually it's you can see here that it's reference for call to Initterm function. Initterm function is pretty cool. It will be executed via the C runtime routines automatically. This is an internal C function, C runtime function, and it's actually responsible for initialization of global variables. Neat. That's pretty cool. So if I understand, there is actually like entry point and initialization of global variables, which in this case, surprise, surprise, will be responsible for the string assigning. Yeah, probably. And what I wanted to mention, yes. You can see it here. There are many. Probably the 172 we already saw. Yeah, so cool. So this is actually some kind of way how you can execute a code before the main, and it will be executed via the C runtime things. Great. So what I would normally do, I would just try to copy that and do some googling. Yeah, but I will try to show you that never, like, don't trust everything what is on internet, even though it's partly true. Yeah, for example, if I would actually do in-term first of all, in-term function, what Microsoft will tell us. Initterm function is internal methods that work a table of function pointers and initialize them. The first pointer is the starting location in the table, and the second pointer is the end location. Great. So start end. You can see this first end. Great. You can see it's actually the end of the table. Super. Blah blah blah. Remarks. These methods are only called internally during the initialization of C++ program. Don't call these methods in a program. Great. When these methods work a table of function entries, they skip null entries and continue. So what happens? that there are many entries. First of all, here you can see that first one is a null. It will be skipped. Yeah, it will be skipped. Yeah, and there are things. If there will be nulls, this will be skipped until the last, which is here. Again, null. Yeah, but there, these will be executed to initialize global variables. Great, thank you, Microsoft. But if I do some googling, Initterm function table malicious code, bam, trend micro. Thank you, trend micro, because there is like C, they call it C++ runtime library code tampering in supply chain. What code tampering? If you scroll a little down, you will find out that they are talking about a showpad. Initterm call entries in function pointer table that entry blah 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 is the malicious one. Well, okay. List of poisoned modified. They call it like table poisoning or something like that. Here it is. Yeah, there is something like this. This is actually our case, yeah, because we have some. We don't have actually malicious. I will explain this difference because there are filter shows the function pointer table of showpads blah blah blah. Initterm function is appointed begin and end. This table is used for constructing object at the beginning of the program, particularly for calling C++ constructors. Correct, which is what's happening in the screenshot below. Function pointer blah blah blah. As shown in figure 2, the function pointer entry labels malicious code, which is here, at the virtual address blah 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 has been poisoned to point to a malicious code. It's more accurate to say that it is the function pointer table that was poisoned rather than the function Initterm. Well, I would normally not state that something was poisoned in this way. It's normal feature of C++ when you are allocating global variables. I will show you how to do it. Actually, like we will try it. But we will also later on ask ChatGPT what he thinks. But again, I would also, I think how Trend Micro thinks about that poisoning of the entry in this function table means that you can always like create an entry in this table if you like create a global variable in C++. But you can assign to it something nonsense and you can hijack the execution of the flow before reaching the main, and if the hijacking of execution is pointing to malicious code, it could be called function table poisoning. Yeah, that's pretty cool. So they are correct. How to create something like this which will execute before the main? Let's start Visual Studio. Visual Studio, we will create some very simple program in C++. I will just show you how you can execute, how you can actually hijack the execution before reaching the main using the Initterm function table, which are responsible for initializing global variables. Console. Here, console, C++, here, next, test app, okay, and come on, it's starting to take some time. Great, we don't need this, close, yeah, and let's start to create, it. First of all, I will create some dummy function like const car foo, and the foo will do what? It will just const car test equal hello world and return test. Great. Now we will do like this, things like this. We will just assign or create our global variable, which will be const car pointer test equal Foo. Great. And now we will use the global variable here, like last. That's it. First of all, this is not poisoning. Yeah, this is not function poisoning. It's like, hey, you are just assigning or using like global variable. You are, and this is actually something what will result that this assignment or initialization of the test local variable will happen in the Initterm function table. Yeah, initialization. So now we can actually poison it a little bit. For example, we will just make a super tricky thing, include Windows header, and we will use here, for example, like WinExec. Okay, so calc and 0. Nice. So what happened? We will just like do something that it will do some assignment. It will do initialize the variable, but it will also hijack the execution, which could we refer as a interim function table poisoning. Yes, correct. Now we need to try to maybe run it. 86, 5. And I don't want here like well, yeah. I will just try it if it works. Cancel, I don't care about symbols. And here is a calculator, and here is a hello world. Okay, it works. Now switch to release because I don't want to have the rubbish created by the debugging, by the debug release, debug build. But I want this. What happened? Don't care, don't care. So we have this. I will try to make release. We need to do some kind of modification because if we just release it or build it in release mode in like this, there will be some inlining and other optimization. So I will just try to reduce this optimization to so it looks like similar like what we have in Amadey sample. So go to C++ optimization. We will turn off the optimization, disabled, inline function def disabled, inlining, larger code, no, war program optimization, no, apply. Now also the linker optimization. And in the linker optimization, we need to use, we will references, no, no, apply, okay, build, and yeah, we have a problem here, not compatible with LTCG incremental, blah, 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 specification link without LTCG incremental. Okay, project, test, properties, optimization, link time code generation, here it is. Let's switch to default. Apply, okay, project, build, and correct. Surprise, surprise, we have it here. Copy and find that binary. Here it is. Come on, release. Copy that here, and let's try to investigate it a little bit in IDA to check it what is going on. Oh, yeah, we can check the debug symbols. Why not? Yeah, so here is main, again, main. First of all, option demangle, because this naming is pretty bad. So you need to demangle names and as a names. Okay. 5, and you can see that here, what we see here is something like Okay, synchronize with pseudocode. We can see that something which is set in the test, which is a global variable, will be printed. Great, super. What is in the test? You can see that it's here from this location accessed, and here is a write in a function called dynamic initializer for test. Great. Normally we would not have this name of function. It would look like the sample in Amadey. Yeah, in the case of Amadey. You can see here that something is going on. Test. Here it's assigned, and this result will be assigned to in function foo, and function foo is what? Win exec calc and return hello world string. Great, but from where this is called? Air data. Air data what? Air data what? And what? Like what? Like hey, you know, from where? Like how is this called? So I think it's actually called from Initterm C runtime function. Like you know, we already so go to the main. Reference main and common main second. We are here main, and before the main there should be some the Initterm function, and it's here is before that. You can see here are the like the range, like from to these functions should be initialized. Yeah, if you check the start, it's like 407000 and end 407300C. If you go to start, remember all 0 entries are ignored till it found some entry pre-CPP initializer. There is okay, another thing. And here we have our dynamic initializer for test. And it will spawn this thing. Great. Super. So it will actually, it resulted in the same, into the same thing we saw in Amadey sample. If we want to verify that, you can actually put a breakpoint here, if 2, and also on the main. Like here. And local Windows debugger, start debugging, yes. Close that. And where we are on the dynamic initializer for test for the global initialization. If you press F8, and here it will spawn our calculator. Great. So we hijack the execution before the reaching the main, and we continue. We are on the main, and now you can still not see anything here. 8, step over, and hello world. And this is about the like function table poisoning of Initterm C runtime function. We could talk about function table poisoning in case we are hijacking the execution. But if there is a really just assignment of global variable, like initialization of global variable, I would not refer to it as a poisoning of table or something like that. But in case of trend micro, I think it was corrected. It was correct to mention that it was poisoned. Last thing I want to show you that I had a chat with ChatGPT, of course, about that. What he thinks about that. So I just asked him in C++ there is an internal function called initterm. MSDN states it is internal methods that walk a table of function pointers and initialize them. How can one program such a function being initialized execute via the initterm? Could you provide some examples? And blah 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 something. Yeah, typical initializer blah blah. Could you provide some example just for initialization of global variable, which is a string, and later used in main method, so the initialization is executed before the main. In the main method, the global variable string will be just printed, and it will tell you this. Of course, here is also the explanation. The Initterm function in C++ is typically used for initializing global variables with constructors or calling functions during the startup or initialization phase of C++ program. Correct. Absolutely good job, ChatGPT. Good job. Here you can see that he also like printed similar things like we created now. Yeah. Here is a global variable string, initialization, and here it is used. And it will be actually like moved to Initterm table, function table to initialize. Also, I read that somewhere this technique was called Initterm function table poisoning. What do you think about that? The term Initterm function table poisoning refers to a technique that can be used to inject malicious code or modify the behavior of C++ program by manipulating the function pointers in the function table used by blah blah blah, something like that. So basically, purposes such as unauthorized code execution or modification of program behavior. Great, great. So Amadey is actually using that to assign string into the global variables. So really for initialization of the global variables. But in case your malware code would use it to hijack your execution, you could refer to it as a function table poisoning of Initterm function, something like that. Blah blah. And that's all. That's all for now. I hope you enjoyed that. It was quite a long because I wanted to cover all those steps, not just the memory snapshotting in IDA Pro. I hope you enjoyed that and see you next time.